Okay, I believe now we are ready. Hello once again, and thank you for joining our workshop, Go from Predictive Modeling to Predictive AI. I'm Kitty Ivanovska, Marketing Program Manager at Kumo AI, and I will be your host today. On today's workshop, you'll have the chance to learn from Jure Liskovec, co-founder and chief scientist at Kumo and also professor at Stanford, Yubo Zhou, senior ML engineer at Reddit, and Blaz Stojanovic, ML engineer at Kumo. During this session, you'll discover how to use Kumo and its AI models for relational data to make better recommender system, risk scoring, fraud detection, and many other predictive AI applications with up 95% less work compared to traditional ML approaches that rely on feature engineering. You'll also learn how Reddit leverages Kumo models to optimize ad engagement. Before we begin, please remember, and this is very important, to use the Q&A section to ask any question throughout the session, because at the end, we will dedicate 30 minutes to answer the most relevant question in order they are received. Now, I believe we are ready to start, and first I'd like to invite Jure to begin this workshop. Jure, over to you.
Yeah, hi everyone. Thank you, Katie. So very excited to talk to you today and teach you how we can change and start building neural networks over relational data and kind of completely change how models are being built, how long it takes to deploy them, and what accuracy we get out of them. So to think what am I talking about is that really the most valuable data businesses have is structured relational data, right? It's data that resides in tables. So this could be a table of customers, transactions, and products, where in the products table we have the product IDs and product descriptions and product images and materials and colors and so on. The transaction, the sales data includes which users bought what at a given time, at what price, with what kind of payment method, and so on. And then for every customer, we may, for example, know their age and location and whether they are a loyalty club member and things like that, right? And this is just one example. But if you are in finance industry, you have loans and accounts and clients and credit cards and so on. And this is, again, interlinked. Or in any kind of social media, we have users and posts and likes and votes and comments and so on and so forth, right? And this is a complex schema of tables, and we would like to build models over this type of data, because this is business specific, most useful data that we would like to learn over, right? Like we want to build models that actually solve our business problems, and models are defined by the data, by our business that is captured in this kind of schemas. So the question is, how do we build relational models over relational data today? And when I say models, I mean applications like personalization, fraud detection, forecasting, customer acquisition, churn, lifetime value, search, retrieval, ranking, and this kind of use cases. Right. So as we have this data in a, let's call it in a database where we have tables linked with primary foreign key relations, and we want to build models for these types of use cases, how do we do this today? And the key fundamental problem that we identified in my research group at Stanford is kind of once you see it, it's obvious. It's like basically the statement that I cannot learn over my tables. Right? There is no AI method today that could just learn over this schema here, over this set of tables, and build me a model out of it. We cannot learn from multiple tables at once. What can we do? We can only learn from one table. So imagine I want to be predicting whether a given user here is going to churn. Let's say churn means they won't buy anything in the next 1 month. How do I build a churn model over this type of schema? The way to do this is to do manual feature engineering. And this is like super tedious and takes super long time, right? Because we don't know how to learn over these 5 tables here. We have to manually be joining them into features. And then the question is, what kind of features do we come up with? And we actually hired the data scientists to say, please, use traditional machine learning tools and build me a churn model on a schema that I showed you. And then the question is, what kind of features does after hours of work a data scientist come back, right? And they say, okay, how many weeks since the first review of the user? How many reviews did the user produce so far? What is the sum of review ratings they produced? What's the average review length? And so on and so forth. And you can see how this is getting complicated and very arbitrary, right? Why, for example, number of reviews matters. Shouldn't we know when was the last review that the person submitted? Why, here are we only looking at the embedding of the summary of the last review? Why not to try to summarize all the reviews? Here we are saying value of the last 6 months versus value of the previous 6-month window to see how the trend of the reviews is changing. Why these particular values? Why these particular cutoffs? It's unclear, right? So, and just to be clear, right, behind every of this feature, there is a quite complex SQL query that we need to run to actually compute this. And this takes a lot of computation. It's very brittle and so on. And, somebody might say, hey, Jure, but this does not apply to me. I'm using embeddings. I'm in the neural network world. And the answer is, sorry, it doesn't matter. You still have the problem, right? Even if you do two-tower, if you do any kind of neural network, you have to bring some features, some description of the object inside that neural network. So for the users, then again, beyond user features, you need to aggregate activity with feature engineering. You need to aggregate transactions. You need to look at all these other things to actually be able to actually apply neural networks as they are today. So what is the bottom line? The bottom line is that we have this beautiful relational data spread across multiple tables, but we cannot learn directly over this data. We have to manually join these tables together in essentially arbitrary ways to create these features that describe, let's say, every user, every customer in our database, and only then we can apply neural networks or kind of classical machine learning algorithms to make predictions. And this is kind of arbitrary, suboptimal, super manual, takes a huge amount of effort. And the second problem is that this is very brittle, right? Maintaining these feature computations, pipelines, stitching together open source tools is a huge headache. And it doesn't scale. It keeps failing all the time. Features get stale. We have information leakage. Our models don't work in production. So it takes kind of 6 to 9 months to put a model in production, right? There is so many different steps about how do we build a model. It's all manual. It's all about feature engineering, productionizing, and things like that. And it takes a long time, even though if we have everything ready, and the models are not that good at the beginning, right? So kind of building this type of models is slow and tedious process. So now, kind of with this introduction, the question is, how can we change the status quo, right? How do we get beyond manual feature engineering over the most valuable business data that we have? And how can we kind of get AI to help us do that? Because if you think about relational data, it seems that AI trends have skipped it. And what do I mean by that? If you think about old school computer vision, in old school computer vision, you took your image, but you didn't know what to do with it. So you wanted to detect some features of that image. You computed Gabor filters, you computed SIFT features to featureize the image, and then you build your classifier, right? And this is exactly where machine learning or model building over relational data is. You don't know how to operate over this complex relational structure, so you are manually building some features and then kind of training classifiers, rankers on top of those feature representations. But if you look at where is computer vision today, where is natural language processing understanding today, it's in a different world. It's in a world where we have neural networks that can learn directly on the pixel values to tell me what's in the image, right? So I don't need to do any feature engineering anymore. I have a neural network that I just point to the raw data. So the question is, where is that neural network for relational data? Why is there no neural network for relational data? Why do I have to be stuck in this, 20 years back where everything I do is manual? And it shouldn't be this way because, AI, computer vision, natural language understanding made a step forward. They developed neural networks that allow me to learn directly on my raw data, right? And that's the step function change that we all want, and we want to get to kind of where the world is, not be stuck in the past. So the question is, right, how do we design AI algorithms that kind of capture the meaning of relational data, that can just learn over a set of tables? I can just point them to a set of tables the same way as I point a convolutional neural network to a set of pixels, or the way I point a transformer to a set of tokens, right? How can I learn over this, right? And notice that your database is not composed of pixels, and your database is not a linear structure with that you can linearize into a sentence, right? It's more complex. It is a set of tables interlinked with primary foreign key relations. So this is the research project we've done at Stanford, and the question we asked in my group at Stanford, and we actually came up with a amazingly elegant solution. And the solution to this problem that I just motivated, we call it relational deep learning. And the key to this solution is to take your databases, essentially think of them intrinsically organized as graphs. And we actually now know how to develop neural networks that can learn directly on the graph data. What is the benefit? The benefit is no feature engineering needed. We are able to learn directly on the raw tables, on the raw rows and columns of the data spread across many columns. So how do you make this work? What are the key insights? There are two key insights. So the first is, for AI to work, you really need to provide supervision. And while in pre-trained models, this kind of self-supervision is obvious and given, if you think about predictive models, supervision is different for different tasks. So we need a very simple way to specify how do we provide supervision to models. And now that I have a way to provide supervision, then the next question is, how do I learn across a collection of tables to get a model for that trained under that supervised task? And if we bring 1 and 2 together, we get much more efficient and much more performant AI models with minimal data preparation, no manual feature engineering, and no babysitting of ETL pipelines. So quickly to tell you, the first insight is supervision is key to AI. And the way to think of supervision, you need a training table. You need a way to say, okay, what are we trying to predict? Are we predicting the next token? Are we predicting whether the person is going to churn? And what's the definition of that? Are we predicting a time series because we are doing forecasting? Are we predicting a set of, let's say, products you are going to buy, and so on? So what we have developed is a very simple SQL-like language that allows you to specify supervision for these tasks. So for example, this language has 3 parts. Has the part of predict, where we set what are we predicting. Then we say, who are we predicting this for? And then we also have a where we can apply various filters, right? So here for customers, transactions, and products, I can say predict whether sum of transactions dot price. So every transaction has a price at which the product was purchased. Let's say between now and 30 days in the future, I'm predicting the sum of transaction prices, and I'm doing this for every customer ID, right? So for every customer ID, I'm predicting what will be the sum of prices of their purchases in the next 30 days. And let's say I'm only doing this for people where count of transactions in the last 30 days, so in the last month, is greater than 0. So I'm basically saying, predict me how much a customer is going to spend, given that in the last month they bought at least one product. And with this very flexible language, I can quickly specify, regression tasks. I can specify classification tasks. I can specify recommender system tasks, ranking tasks, and things like that. And the key is that now with this specification, we can automatically interpret this language and generate the training labels, essentially the self-supervised labels, which we are then going to use to train the neural network with. So now the second question is, what kind of neural networks actually are able to learn across the data that is spread across multiple tables. And the key insight to make this work is to realize that structured data is a graph. Okay, so that you can take your set of relational tables and essentially you can look at them, you can view them as a graph. Okay, so as a graph of entities being interlinked. So every customer is a node, every transaction is a node, and every customer is linked to all their transactions, and every transaction is linked to all the products that include it, and so on. Okay, so why does this matter? This matters because we can just start with a set of tables, and the platform can intrinsically represent that as a heterogeneous temporal graph. As I said, every table defines a node type. Every row in every table becomes the node. The columns in that table becomes the attributes or properties of the node. And of course, then we have the edges, which are the primary foreign key relations. And notice that these edges are actually time-stamped because in our case, each transaction has a timestamp, so each purchase has a time. And this is very important because if I'm predicting how much somebody is going to buy next month, I need to know what is the reference time right now. Okay, so that's the first thing that is part of the solution. And then what's the second thing? The second thing is that, you know, we actually know how to build neural networks that can learn over graphs without any feature engineering. And that approach is called message passing neural networks, MPNNs, people call them graph neural networks, and people call them also graph transformers. But essentially, the idea is the same, that once you have taken your set of tables, internally represented them as this heterogeneous temporal graph, you can take, you know, you have nodes, stores, products, transactions. Every product, for example, has a set of properties. We can use various kinds of pre-trained models to encode those properties like description, image, material, color, and so on. And then really where the magic happens is this, what we call the sparse cross-attention mechanism, where if we are predicting whether this lady is going to churn, we won't only predict this from her age and let's say location where she comes from, but the attention mechanism is going to attend across the graph. So it's going to attend across all her transactions. So by this, the neural network will now learn what kind of pattern of transactions leads to churn. The neural network is going to attend over all the stores this lady visited. So if there is a pattern of stores, or if there is a particular dirty store, let's say, that leads people to churn, the attention mechanism can learn that, right? Similarly, the attention mechanism attends over all her products. So if there are properties of products, if products are faulty, the attention mechanism can learn that, right? So it's a neural network that is now kind of spanning from one table to another table, right? To go from customers to transactions to products. And we can see this here in as kind of multi-hop attention across this graph, right? So what have I just achieved? I have now a neural network that can learn directly over my data. And the point is that this is fully general, right? I can apply this to any kind of supervised learning task. Classification, maybe I'm doing next best action, I'm doing customer churn, regression, I can do lifetime value of a user. I can do also link level tasks, which would be kind of this two-tower type architecture. So when I'm trying to predict some kind of affinity between, you know, a left-hand side item and the right-hand side item, between like recommendations, product affinity, expected revenue of a user store type pair, and things like that, right? So that's the exciting thing, that this is fully general. And then the other thing I would say is it also supports many different architectures that can be built on top of this framework that can directly learn over your relational data. So many different architectures and use cases can be supported on top of this basically graphical representation of your structured data. So you can build kind of two-tower models that are graph aware. You can build shallow type models with embeddings. You can build other types of models as well. And you know what's the key? The key is to really think about how is the information being propagated over this graph, right? And how, when we are predicting something about the user, we also want to attend over all the transactions of the user. We want to attend over all the products that the user has purchased. Then we can actually go back and say we also want to attend over all other transactions that this products participated in, and all the other users who have purchased those products. So we can kind of get this collaborative filtering type effects. And you can see as the neural network is essentially exploring the structure of this graph, it can learn signals that would be very hard to put into features. So we really go from this, every user is an IID training example and has nothing to do with anything else, to really think about this kind of multi-hop reasoning across the tables, across my entire graph of my data. And this is where this magic happens, and where these new, much more powerful signals are being learned with the neural network, rather than a human kind of manually engineering features and hoping that these features somehow do the magic. So this is what I wanted to say, and now I'm going to hand it off to Blaz to show you some of this technology and this theory in action in a system that is scalable, production ready, and allows you to actually start building these accurate models very, very quickly. Blaz, over to you.
Thank you very much, Jure, for the wonderful presentation. So hi, my name is Blaz Stojanovic. I'm one of the applied machine learning engineers here at Kumo. And today I'll be walking you through a very brief use case of what it looks like to use Kumo in production, right? So we will be focusing on building high quality embedding models in Kumo. We will be working with a data set of users, games, and interactions between them to do so. We will train a relational deep learning model, which produces user and game embeddings in the way that Jure just described. So we will be primarily working in the Kumo SDK, which is the window you're seeing right now. But I will also be referring to the Kumo UI at relevant points in time, right? So let's go ahead and get started. The first thing we want to do is we want to prepare the Kumo SDK environment. And this we do in two steps, right? First, we pip install Kumo AI, which is a Python package that allows you to interact with our product, and we can then import it as Kumo. And secondly, we initialize the Kumo SDK against an existing deployment of Kumo. And by the way, Kumo is free to try. So if you want to apply and try this notebook yourself, or even try with your own data, we will give you this environment URL and API key to get started. Okay, so with that out of the way, we can go ahead. And as with any machine learning, we always have to start at the data, right? Now, Kumo provides many ways for you to work with your data. Today, we're going to be focusing on a very simple case where the data resides in an Amazon S3 bucket. So we have it stored in Kumo public datasets. You can access the data yourself. We can create a Kumo connector to connect to this data by providing it the root directory. And immediately we can see the different tables, or rather table names of the data that is stored there. And there's many here. So you have channels, content, game purchases, game sessions, games, quest interactions, etc., etc. We're not going to be using all of these, but it just gives you a bit of flavor of what type of data you can bring into Kumo to build models, right? And this is very representative of a schema you might see in the real world. So by establishing the connector to the underlying raw data, we can inspect what is in this table. So here's 5 example rows from the users table. And we see that we have the user IDs, the create account dates, etc., etc. Now, this is all random data to illustrate a case, but Yubo will later present, or rather show that this actually works on real data as well. But we can likewise inspect the data for the games table and the game sessions table, for example, right? So we have a user ID, which plays a game ID. We have the timestamp of when that session started and its duration, right? So at this stage is where an engineer would kind of perform initial data analysis and perhaps even perform some type of data transformations if necessary. And of course, Kumo SDK can be launched, or rather run from a place where a data engine like Spark is available, and you can do the transformations you need to perform to get the data ready. But once you're kind of done with that stage and happy, you can start by creating Kumo tables, right? Now, what are Kumo tables? Kumo tables are views of the underlying data, but they contain additional metadata and information such that the Kumo machine learning platform can accurately and precisely define machine learning models with the predictive query language. Concretely, this additional information includes the column data types. So that's the D type, and the column semantic type. These allow the models to understand how to process the raw data into its vector representation, the table's primary key if it exists, and likewise the time columns in the table. So that's kind of start and end time in the table. Just as an example, the users table we can define from the underlying source table by providing the source table directory to the connector and defining this additional metadata. We also provide many utilities to make this simple, right? So for tables which have many columns and you want to very specifically tune the user S types and D types, you can call users.printDefinition, which prints out the definition for the table, and you can paste this as a definition back into a following cell. You can also kind of on the fly modify S types, D types, primary keys, etc., any type of metadata of a table until you're satisfied with its configuration, right? And this is the process of onboarding one table, and we can repeat this for the other tables in the relational in our relational schema, right? So the tables we're going to be using is the users table, the games table. Those will be our kind of primary entities of interest and entities we want to create embeddings for. But we will also add kind of interaction data between games and users into our graph. So we're going to have the game purchases, so users who purchase games. We're going to have the game sessions, users who play the games. We're going to have quests associated with games, and users can interact with those quests as well. And all of this data will be taken into consideration when we build the final embedding. Now, any object that we define in the Kumo SDK, we can also view in the Kumo UI, right? So those are two sides of the same product, and they're meant to be used in unison. So any type of object in the SDK, you can just call .save, and you can save and view it in the UI. So let me actually open the Kumo UI, which you should be seeing right now. Now you see there's some data already here, but if we navigate to the tables pane, we should be able to see the tables we have just saved, right? So these are the users game and game purchases tables, and we can go on from here and inspect individual columns, right? So and likewise all of the relevant metadata as well. Okay, so that's kind of the core process of adding the Kumo tables. Now we can continue our work in the UI, but I will proceed in the SDK just for clarity. Just one final note. Of course, any object that we also create in the UI, we can load in the SDK as well, or we can even take an uploaded object in the UI, change it, and download and load it in the SDK and work from there. So it's really very flexible. Once we're satisfied with our Kumo tables, the final step in the data processing pipeline is to create the Kumo graph. And this is the graph on top of which the model is defined. And it's kind of the final step in our pipeline to process the data. And defining the graph is very easy, right? We just need two things. We need a dictionary of table names and Kumo tables, right? These are the tables that we're going to include. And we need a list of edges that connect those tables. And an edge is just a tuple of the source table, the foreign key connecting the source table to the destination key and the destination key. So just as an example, right, we have this game purchases table, and we have the users table, and we will connect them via the user ID, right? So the user ID must be present in the game purchases as a foreign key, and it must be a primary key in the users. And this is kind of the data processing done. We can, of course, go ahead and visualize this graph. Actually, I'm going to remove the column display just to make it a bit more clear. So this is the graph we defined. We have our users, graphs, and quests, and these are connected to different facts or different via different interactions, right? So the user can purchase games and can play games. Games can be played or purchased, or can be a part of a quest, and then that quest can be interacted with by the user, right? So this is a very holistic picture of the data. And just to reiterate, likewise, like saving the tables, we can go ahead and save the graph as well. And if we navigate to the UI and go to the graphs page, we should be able to see the user game graph here as well, right? So this is just the same graph that we have in the SDK as well. Okay, so once we have prepared the graph, the next step is to actually go ahead and focus on the modeling. As Yura mentioned, Kumo allows us to define models directly on this graph representation, and does so through the relational deep learning framework. In this framework, the predictive query, which is a domain-specific language, is used to fully specify the model, right? But at this point, it's a very good time to pause, because it's very important to understand what we want to predict in the first place, right? So to reiterate, our goal today is to create powerful user and game embeddings such that they hold predictive power for downstream tasks. Now, Kumo provides state-of-the-art methodology for producing supervised embeddings, quote unquote, right? These are embeddings which are generated as an intermediary step in a predictive task that is supervised by some signal. And that supervision is very essential for producing good embeddings, right? Because it kind of focuses them to have predictive power. Otherwise, they don't perform well in the predictive task. So what I mean by this, we want to generate embeddings, or we want to build user and game representation in embedding space such that the distance between user and game in the space is predictive of a user-game interaction, right? So specifically, this means that users and games in this space that are likely to interact with each other are very close. And this has very powerful extensions to both sides, right? Because not only are user and games that are similar together, but similar users are similar in this space to other similar users based on the interaction we supervise on. And likewise, and vice versa, games are similar, right? So similar games, these are games that the same user is likely to interact with, are also close in this space. And this has very, very important, very powerful implication for downstream models. And if you notice, I wasn't very specific, so I was saying interaction this whole time, because we can supervise these embeddings in many different ways. So even just in our graph, we can supervise embeddings either by trying to predict which games will be purchased by which user, or which games will be played by which user. And these will give us slightly different embeddings that can be used in different ways downstream. So now that we've kind of put this theory part out of the way, we can go ahead and define a particular task which will allow us to do this. And this is what we call a link prediction query, right? So in the graph representation, we want to predict the links between user and games. And these links have to be of specific type. So here's how we define the predictive query in Kumo. It's very simple. We just pass the graph and we pass the predictive query, which is a string here. And I'll just read it out and then I will break it down, right? So we want to predict list distinct game purchases dot game ID over the next 21 days. And we want to rank top 50 for each user ID. So this is very easily understood if we read it backwards, right? So for each user ID, we want to predict a distinct list of game IDs such that this pairing of user and game ID will be very likely to appear in the following 21 days. And if we go ahead and validate this query, we see that this is a temporal link prediction task. Right? And this fully specifies our model on this graph. So the next step is actually to just train the model, right? Now the predictive query object in the Kumo SDK has two main roles, right? So it defines the model, but it also generates the training and prediction tables. We will be following this top path today, at least initially, because we have to create the training table to train our model. And this is actually very simple, right? So we can use the query object to suggest the training table plan. We can then print it out. And I won't go into detail here, but all of these knobs can be modified. And then it's very, very simple. We just call query.generate training table by providing the training table plan and using this non-blocking keyword. So any job you launch in the Kumo SDK can be launched asynchronously, right? And this is very useful because it allows us to string together many different jobs and just makes our lives as machine learning engineers or data science practitioners much easier, right? So this is now launching a training table job. And if we navigate to the UI, at its core is the jobs page, right? So once that the Kumo SDK runs the prediction, the training table generation job, we will see it appear in the jobs page as well. So that's going to go on backwards. It's going to be happening in the well, that's kind of going on and happening in the background, we can go ahead and focus on the training portion. So after launching a training table generation job, we're ready to train a model with that training table. For that purpose, we need to create a trainer object, which is then pass the graph and the training table to either fit the model or make predictions or embeddings. Those are kind of synonymous in this case for this particular model. To do that, we first specify a model plan. Now, this is kind of a mirror of what we did with the predictive query, right? With the training table, we specify the training table plan first, and then we can edit that plan and launch the job, right? So I think the job should be launched now, so we can refresh the jobs page here, and we should be seeing a training table generation job in the Kumo UI. Here we see the training settings, and this is generating the training table job for our predictive query in the background. In the meantime, our model plan has also finished in the UI, and we can print it out and inspect. Now, it's a big search space, and I have a very short run through the notebook today, so I don't have time to go into detail, but suffice to say, it gives you very fine-grained control of what the models are in Kumo. Now, one particular aspect that was already mentioned by Jure and will be further elaborated on by Yubo is that you can build several architectures on top of this relational deep learning paradigm. And specifically for link prediction, we provide you with 3 options, all of which have their own advantages and disadvantages, and we'll see which one Reddit chose for their purposes later. Now, after the model plan is finished, you can modify it, and once you're kind of satisfied with it, you can go ahead and use that model plan to define a trainer object, which you can then use to train the actual job. So this will now launch the training job, which will train the model end to end. And once that model is finished, we can use it for creating the embeddings. Now, let me print out the training job ID. So I'll just take a look here and copy it. There's another functionality. So for any asynchronous job, you can attach to it just to see its progress. So we see that the job is currently waiting to start, and we can also click on the link here and see the actual training job in the UI, right? So this provides you with kind of crucial information to monitor your training jobs and make sure they succeed in the way you want to. And of course, at individual training job, because we pass job futures into it, depends on 2 things. It depends on a refreshed version of the graph. This is the graph we created initially that is kind of being materialized in the background, and the training table, which will be created from this graph. Right. And this is kind of the end-to-end flow of starting a training job. Now, let me show you an example of yesterday's job I ran that is finished, right? So it ran for about 40 minutes, and you can see the query, you can see the finished snapshot and the finished training table generation. You can see the model performance, you can see the evaluation, and you can see the explanation as well. So we provide extensive kind of explanations for all of our training jobs as well. Now, there's one final step, which is that you can actually make predictions after the training job is finished. And why not just do this in the UI, right? So of course, there's a programmatic way that is very similar to what we did for training, but we can just launch a prediction job from the UI as well. And here here we just pick a finished training job. We select when we want to predict for, how many parallel workers we want to use, output destinations, kind of what type of artifacts we want to output. So today we're focusing on embeddings. We would need to specify the output directory, and then the output would be placed there, right? And we can launch this job from the UI as well. So this is kind of what the end-to-end flow looks like. In the SDK, we can also load kind of all jobs and make predictions out of those. But that's kind of operational aside. So that was kind of my portion. So I showed you just a single example. Actually, there's many more examples of such notebooks available if you visit the documentation page on our website and navigate to examples. So in particular, I show you a game purchase prediction example but there's 8 other examples of predictive tasks end-to-end in Kumo SDK for you to use. And if you want to get started today, you can just click start for free, or you can navigate to kumo.ai/try, fill this out, and we will provide you with API key and a deployment URL for your Kumo environment. So yeah, thank you very much for this, for listening to me. And now I'll hand it off to Yubo to present his part. Thank you very much.
Hey guys.
We can see your screen, Yubo.
Yeah, can you all hear me now?
Yes, great.
Hi everyone, and thanks for joining. My name is Yubo, and I work on the ads machine learning team at Reddit. Today, I'm excited to share how we leverage graph embeddings and graph neural networks to improve our ads recommendations at scale. Graph embedding has delivered one of the biggest lift out of any individual features we added to our CTR model last year. And this is a great example of how to applying graph embedding or graph neural network in your own applications. By the end of the presentation, we will also discuss several challenges we have encountered during the practice. To start, let's look why Reddit is a great fit for graph-based models. Reddit is in here today a massive social network where entities like users, hosts, advertisers, and subreddits form a highly connected graph. These entities interact through many different types of edges, such as comments, upvotes, clicks, messages, and video views. Our predicted click-through rate model, aka PCTR model, select which ads to show to user, and is one of the most important models of the ads team. This model predicts the probability that a given user will click on any given ads. If we increase the accuracy of the PCTR model, we will improve both user experience, relevance, revenue, and advertisers' value. So why did we want to use graph embedding? In short, many type ads company has used this technology, seeing CTR and revenue gains worth hundreds of millions of dollars annually. Inspired by those successes, we kick off a project to integrate graph embedding into Reddit's click prediction model. Here's a high-level view of our approach. We first construct a massive graph covering our entire active user base. On this graph, we use Kumo AI to train a GNN model and then export the model embeddings. Next, we train the PCTR model. The PCTR model merges the GNN embeddings with hundreds of other features all together and feed to the prediction model. Finally, the PCTR model is deployed in our online model serving infrastructure in order to make billions of calibrated click predictions in real time. Let's break this down further. Our graph schema contains 3 entity tables: subreddits, users, and ads, and 4 event tables: visits, video views, long clicks, and clicks. Each row in every table corresponds to a node in the graph, and each foreign key relationship corresponds to an edge in the graph. So we end up with a graph with billions of individual nodes and edges. We use Kumo to train a link prediction model, and we supervise this model using one of the event tables, such as the long click event. In effect, we treat each long click event as a positive example and uniformly sampled negative examples from the entire ads data. So what model architecture did we use? Kumo AI helped us create a fairly sophisticated GNN model architecture with only a few days of work. The left side of this diagram creates a user embedding. The model performs a random walk of all the nodes surrounding each user, taking a raw feature in each node, and then use GNN aggregators to consolidate this into a single user vector. This means that all of the data connected to each user are used to generate the embedding, including connected subreddits, historical clicks, video views, and even other users. The right side creates the ads embedding. For efficiency purposes, we use a simpler architecture, a combination of text and image embeddings, as well as a lookup embedding that are learned through backpropagation. At the top, we take the dot product of user and ads embedding and optimize this through softmax. It would normally take several months to build this model architecture using open source tools. However, since many of those modules are already built in Kumo, it only takes a few hours to experiment that. It's very handy. To ensure our embedding capture meaningful structure, we export the embedding into a Python notebook and analyze them further. In this video, we will demo the analysis on subreddits embeddings. This video visualizes 10,000 subreddit embedding use TSNE. This manual inspection gives us confidence that our embedding preserves meaningful relationship between all of entities. For example, as you can see from this video, you can see that subreddits from fairly dense clusters around specific topics, such as games, sports, countries, or hobbies. We will talk about some challenges we have encountered in practice. In these slides, we will discuss the data leakage problem. Those boxes represent the date coverage of each data set. One of the biggest pitfalls in machine learning is data leakage, where your model accidentally learns from a feature that are not present at serving time. Initially, we accidentally trained a leaky model. We trained the embedding on data overlapping with our CTR model's training period. That means we have an overlap between the red area and the yellow area. This led to a severe overfitting. By editing the training config in Kumo, we were able to ensure that the GN only used data from earlier data period, preventing any information leakage problem. Another topic is about the noisy data and the label qualities. A major decision in training GNN is which edge to supervise on. Because Kumo made it easy to experiment with different predictive targets, we tried training models on both click events, as well as long click events and short click events. The term short click often implies unsatisfied interactions, and the term long click implies deeper engagement, adding richer user intent signals to the PCTR model. Ultimately, we learned that long click events produce higher quality embeddings. Even though long click events are 10 times sparser, but they provide a stronger positive signals about user engagement. As a result, we actually saw 2 times more lift for certain metrics during the A/B test. If you're interested in learning more, feel free to check out the Reddit engineering blog. My colleague have published several blog posts detailing the architecture of our PCTR model, as well as the design of our ad retrieval and ranking system. Also, I'd love to continue the conversation. Feel free to contact me on LinkedIn. Thanks for attending and happy to take any questions. I'll hand it over to Katie.
Thank you, Yubo, and thank you everyone for sharing your knowledge and practical examples. Now we'll begin answering the questions we received one by one. For any question we don't have time to address live, we will follow up with you via email. So the first question is, please explain about data store space. I will invite our speakers to take the first question. Yura, Blaz, Yubo.
Yeah, we can explain. I'm not sure what would that mean, but maybe the way the platform works is that it basically is, and there are a few questions later asking about this. So the platform connects directly to your data warehouse. So if you're using Snowflake, you are using GCP like BigQuery, Bigtable, using Databricks. Basically, the platform can directly connect to the tables that you have in your data warehouse. And then build graphs and models on top of that data. It also supports any kind of tables serialized into Parquet format that you can put in S3 buckets and things like that. So that's, I think, what I would say around this question.
Thank you, Yura. The next question is, do you have experience with noisy graphs that are automatically extracted from unstructured data?
Yeah, you can. We work quite a bit with unstructured data as well in Kumo, and definitely you can apply the platform to noisy graphs. Even, for example, if you think of it, even what Yubo was presenting, right? There is a kind of, in sense, a lot of noise in the way customers behave. I know you mean more noise like in the linkages and so on, but that's exactly the benefit of our approach, is that we are learning across all the links and we put every entity in the context. So there can be quite a lot of noise in the structure of the graph, but the platform or the approach is still able to build quite accurate models.
Thank you. Next question. Can I connect to multiple data sources simultaneously? And if so, how does it manage cross-source relationships?
I can explain. So we give the user complete control to define to select the tables and to define the linkages. And that's actually part of the data modeling process, even as Yubo was showing, right? There are different tables, there are different types of linkages between them. And also, kind of as he was saying, part of the modeling process is to add different types of tables, different types of signals, train different models and see what works better and what not. So, to specifically answer your question, you can connect multiple data sources. It's up to you as a user, as a data scientist, as the domain expert, to define how you want your data to be connected.
Thank you. Next question. Does the framework automatically handle event tables where often there are nested event properties per event and we may want to differentiate across them?
Good question. So I assume this means you're asking if your tables include kind of hierarchical JSON nested into them. Is maybe the way I would interpret this. I would interpret this question. So you can definitely do that, right? And it's no problem if you have multiple types of events and things like that. The platform will still learn nicely over them. I don't know, Blaž, would you add anything?
Yeah, there's different ways to structure this in the graph. And maybe it depends on use case to use case what works best, but definitely we support this. It could be either in the same table with many columns, or it can be separated out into separate tables. So should not be a problem for us.
Thank you. The next question is Kumo using only embeddings from the relational data to train and predict the target?
As opposed to what? Yeah, I don't know. Like, not sure if I understand the question well. Go, Blaž. Maybe you do.
I think a good way to think about it is at some point, yes, we only use embeddings to make the prediction. That's kind of the last layer of the first embedding model. But in order to produce that embedding, Kumo takes account all of the data, like the whole graph associated with a particular entity. On one of Yura's slides, where he was explaining graph transformers, you could see this, right? So all of the interactions, they end up in a single embedding, which is then used to make the final prediction. And that's the embedding you can also export and use elsewhere if you choose to.
Thank you. This is a long question for Jure. Jure, have you tried linking this architecture to unstructured stream of data, saying use data stream, then employing architectures that auto-generate? Probably, Jure, you can see the question in our Q&A section. That auto-generate the relational tables and trigger the relational graph architecture you have created, thus integrating an end-to-end learning, optimizing the relational pass-through depending on the key data dimension, then evaluating the effectiveness, the stability of the output, and effectiveness in passing through a relational framework rather than trying some unstructured graph-to-graph or other methods.
Yeah, I think that's a great question. We see quite a bit of use cases like this, where like I would say two things. First, working with a blob of text is very suboptimal, and converting that, still having it in the model, but also adding the broader relational structure to it leads to much more efficient and much more accurate models. So we've seen use cases like that, and we've seen nice wins with this type of approach. I think it's really, this transition from saying every training example is independent from all other training examples, which is what the machine learning 101 or statistics 101 always tell you. They say there is this hidden distribution from which the data is sampled independently, identically distributed, IID, and then you get to learn over it. But the world is different, right? Things are not independent. Things are connected, right? If you think about Reddit, my experience is not independent of your experience. My experience is a function of your experience. It's a function of your comments. It's a function of your posts. It's a function of subreddits you created, right? So I think it's really this fundamental shift from not thinking of things being independent, but really thinking of things, of entities, as being interconnected, as being kind of in the context of the entire world, in the entire environment, right? And once you put things in the context, which means you link them to the rest of your ecosystem, you can build much more accurate models on top of that. And that, I think, is the shift, is from saying, oh, everything is independent and does not interact with the rest of the world, by saying, no, everything interacts with the rest of the world, and the rest of the world provides that context for that behavior, for that entity, for that prediction. And because now you can kind of be borrowing the information from the links, from the context, this means you can learn much more effectively.
Thank you. We have 1 minute until the end of our workshop, but let's answer one additional question. Similar to information leakage question above, does Kumo have inbuilt features to accommodate differences in user-level access privileges to underlying data sources?
Yeah, maybe let me answer this question, and also answer, I see a lot of people are asking about information leakage. They ask about dynamic graphs, the temporal nature of the problems they're trying to solve. And the beautiful thing in Kumo is that time is a primary it's a primary class citizen, right? So it's a first class citizen. So what does this mean? It means that you can beautifully learn over temporal problems, where you have sets of events and you're trying to predict into the future. And because your events are time-stamped, this means that Kumo models automatically will never look into the future. So you won't have kind of nasty information leakage bugs. The other thing we have is very good explainability and model diagnostic features, so that you can, if you have kind of columns in your data that are generated from the future, but you don't know about that, actually we have tools that very quickly allow you to spot those columns. You can remove them from the models, so that your models really learn from the past to predict the future, right? And usually in practice, And again, I think the Reddit use case is a beautiful example, right? You have all these problems where your features might be stale. Maybe you update the features, by the 1st of the month, but now it's last day of the month. So your feature is 1 month old. And of course, it doesn't carry the information it need be. So you would need to update your feature every day, every minute. And that's very wasteful. Right. So in Kumo, you don't have that problem. And then the second problem is that sometimes you update the feature at the end of the month, but you are making a prediction at the beginning of the month. And, knowing the future and predicting the future from it is a trivial task. And we see a lot of bugs practitioners having and problems having in the real world. With Kumo and with this relational deep learning approach, that basically gets eliminated. So you don't get stuck in these bugs and debugging and figuring out why does my offline model not work online. Usually the answer is, oh, your features are stale, your features are wrong and things like that, right? Here, you just need to supply the raw data, the dynamic raw data, accurate timestamps, and the rest is taken care of you.
Thank you.
So those are, I think, my final words. And thank you for all the questions and great insights.
Thank you so much. We've received the amazing question. And now Blaz contacted me. He wants to answer 2 questions that we received in our Q&A section. So Blaz, the first question is, I have been playing around with deep graph Infomax approaches, which gives good results for any problem, but I still had to define my features. So if my understanding is correct, Kumo could help me speed up the process. Also can text me embeddings built using LLMs be directly computed with Kumo. Blaz?
Yes. So yeah, that's a great question. Now, irrespective of the graph approach that is being used, so Kumo is kind of a generalization here and can help you. One of the powers really of using it is that you don't have to throw away any node or edge features, right? So Kumo does all of the feature encoding for you. And yes, that does also include embedding features. Now you can bring your own kind of as embedding columns, or you can use our internal embeddings for that purpose. And these are all documented in our docs page.
And the next question is, in many cases, there are missing data. This will lead to missing node features. How does that impact the learning? Have you seen any practical cases where missing data impacted the prediction quality?
Yes, so missing data, of course, is very crucial, and it's kind of a crunch. It poses problems for all machine learning problems, but I would argue, in fact, that graph learning makes this problem less severe, right? Because in the usual tabular approaches, what happens is you create the features, right? And then those features might be poorly defined because some data is missing, or you might just have missing features for different users. While in the graph learning approach, as we described it, there is no such problem because that's just the way it is, right? So you have a graph and maybe for 50% of users in the graph, there's a feature missing, but the model learns end-to-end on such data and is kind of learns to optimize or hedge against features that are often missing. So that therein lies our advantage, actually.
Thank you, Blaz. Thank you to Yubo, and to Yura. We've reached the end of our workshop. Thank you all for joining, and I hope you gain valuable insights. To request a free trial, please visit our website or reach out to me. Additionally, we are planning another workshop this month, and we will keep you posted. As I mentioned in the chat, we will send you the link of the webinar, the video of this webinar, and also the link to the notebook. Thank you once again for your time and attention, and have a great day. Thanks.
Guys.